Okay, and welcome to week 4, lecture 10. So far with our discrete random variables, we have numerous ways of representing them. First of all, we have the probability mass function, which gives us the probability that our random variable equals a certain number. We have the CDF, the cumulative distribution function, which tells us the probability that our random variable is less than or equal to a pre-specified number. We've also looked at measures of location, like expected value. We've looked at measures of variability, like the variance. And we've also looked at bounding probabilities and stuff like that. We've also been introduced to some of the classic discrete random variables. But today I'm going to introduce you to a new way of representing your random variable, and that is a thing called a moment generating function. Now you might ask, well, why do we need this new way? Well, first of all, the moment generating function will do exactly what it says on the tin. It will generate moments for us. So we know, remember that the kth moment is of a random variable y is the expected value of y to the k. And we can use that to get variances, means, etc. And the nice thing about this function is it will give us a very quick way of getting it. The other nice thing about the moment generating function is as long as it's defined within a neighborhood of 0, it's like a fingerprint for a function. That is, for most functions, if you give me the moment generating function, I know what type of random variable it is. For those who've done other maths, it's quite equivalent to the Laplace transform of your function, if that makes sense to some of you. Don't worry if it doesn't. But think of it as a fingerprint. And we'll see later in this course where we will do techniques where we will find the moment generating function and then basically look at moment generating function and go, oh, that's that distribution. It's used a lot in statistics. So let's just remind ourselves what we've got. So here's our definition. And we've got the moment generating function, and we denote it by m of t. Occasionally, if I want to be a bit more precise, I would, for example, put a little y underneath there, so the subscript will tell you the random variable. And notice this is a function with a single argument that comes in, which is t. And how do we define it? So first of all, I use this to define it, and it's the expected value of e to the ty. And there's certain things that we're not going to worry about in this course where it has to be bounded, it has to be unique, and things like that. Generally, don't worry about that. That is just, to make sure it's sufficiently nice. Most of the stuff we're going to look at is going to be fine. So we're going to start off, we're going to show that the moment generating function of the Poisson, we're going to show that it's this. So let's actually go ahead and do that. So we're going to have the moment generating function of y. This is going to be, by definition, the expected value of e to the ty. Well, just because it's a whole new thing, it doesn't mean we throw everything else. If I want the expected value of a function, what do? Well, because it's discrete, we will add over all possible values. So because it's Poisson, it goes from 0 to infinity. We write the function, e to the ty. And then we're going to write the probability mass function, which in this case is e to the minus lambda to the y over y factorial. Right? So what do we do next? Well, we're going to simplify this if we can. First of all, we're going to notice that there's an e to the minus lambda that can come out the front. What do I have left? I have y to the 0 infinity. We can put together, we've got something to the power y and something to the power y, so I can write that as lambda e to the t to the y over y factorial. And at this point, you can say, well, what do I do now? Well, it's a good thing to remember some of your series that come up again. And in previous courses, you may have been told about a thing called a Taylor series. And a Taylor series is a way of representing a function as an infinite sum. And so, for example, we might have been told before that e to the x, I can write this as a summation. K equals 0 to infinity, x to the k over k factorial. So this is the Taylor series representation of expectation. So, looking at that, if you look over it on this one, if we've got a y, I didn't quite want that, never mind, oh, there's the right button. We've got our y instead of k. This is our x, everything matches. So what we've actually got here is e to the minus lambda, e to the lambda, e to the t. Now that's getting complicated. We've got e to the e's and stuff like that, but it's just using that Taylor series. And if we put that together, we get e to the lambda, e to the t minus 1. That is our moment generating function for the Poisson. So I said it's a moment generating function, so there should be a way of generating moments. And the way you do this is, what you do, if I wanted the kth moment, I take my moment generating function and I'm going to differentiate it with respect to t k times. So if we look here, this is what I've done. I've taken my function and I've differentiated it k times. And then once I do that, I just set t equals to 0. And what I get is my expected value of y to the k. Now, where does that come from? Well, if we go through and we look here, I've actually shown you a proof of that. And the key step in this is we're going to differentiate. Here's my moment generating function. Then all we do is I'm interchanging these two things. And that thing I kept going on about, it's got to be sufficiently nice. It lets me do that. And the nice thing about e to the ti, if I differentiate it numerous times, I just get I to the k. And now when I set t equals to 0, this becomes 1. And we basically get our moment generating function, the expected value, the moment that we want. This is a really nice thing. If you think about it, differentiation, you can train computers to do it. You could just go, here's my moment generating function, just differentiate it. Computers can automatically differentiate. You can get all your moments out really quickly. And differentiation is so much nicer than dealing with all. Remember last time we did the Poisson, we had to mess around with summations and stuff like that. Now I just differentiate, set to 0. So let's see an example and see if we can get that to work. So what we're going to do is we're going to take that moment generating function we just got, and I'm going to get the expected value and the variance from it. So first of all, let's remind ourselves my moment generating function, which is a function of t, is e to the lambda, e to the t minus 1. So the first thing I'm going to do is I'm going to differentiate that once with respect to t. Well, if we differentiate that with respect to t, you should get lambda e to the t times by e lambda to the e t minus 1. How did I do that? If you want to go and recap in first year, go and remind yourselves about the chain rule. Roughly, I'm using the fact that if I differentiate with respect to x, e to the function of x, basically I should get g dash of x, which means I differentiate that e to the g of x. So hopefully you can see that if I take lambda e to the t minus 1 and differentiate it, I get lambda e to the t, because the minus lambda just disappears, and then I rewrote my function. So now let's set that t equals 0. So I get lambda e to the 0, e to the lambda, e to the 0 minus 1. Well, e to the 0 is always 1, so you've got lambda times 1, e to the lambda 1 minus 1, which is basically lambda to the E0, which is lambda. So we have the expected value of y equals lambda. Okay. Now, we're going to have to differentiate this again, so I'm going to quickly remind you of our product rule. Which basically says, if I differentiate with respect to x, a function, it's a product, so I've got g of x and f of x. What you do is basically you write that as a sum of two things. First of all, you differentiate your g of x, and then you multiply that whole thing by f of x, plus you write your g of x and you differentiate your f of x. Or in quicker notation, you can say f of g, if I differentiate the whole thing, where my little tick there means differentiate, is equal to f differential g plus f g differential. Okay, so what does that actually mean for me? We're going to find that if I do with respect to t twice, I should get lambda e to the t, e to the lambda e to the t minus 1, plus lambda e to the t squared, e to the lambda e to the t minus 1. Now, as always, you know that I'm usually a bit shoddy and get it wrong, so please check that product rule, but hopefully that works. So now we will set t equals 0, and this whole thing should collapse down to lambda plus lambda squared. And so that means that the expected value of y squared equals lambda plus lambda squared. And finally, the variance of lambda equals the expected value of lambda squared minus the expected value of y all squared. So that's lambda plus lambda squared minus lambda squared, minus, which is lambda. Okay, so you sort of choose your favourite. I must admit, I have to always practice and remind myself, but differentiation is pretty, algorithmic. You're just some standard rules you have to learn. The rules so far, and go and remind yourselves of these from first year. The chain rule is really good, and the product rule, they're the two ones we're going to be looking at again and again. So at this stage, I definitely recommend you go and do some recapping of differentiation, especially exponentials. We're going to be using that again and again and again, so go and practice that. Go and remind yourself about the chain rule and the product rule as well. If you're not sure about those, I'm always happy to record a video for you, but the Khan Academy probably has some really good reviews of that. And what I might do, if I remember it, is I might shove a couple of links on Piazza so you can see how we're doing. So that's lecture 10, moment generating functions. Very good for getting expected values and variances, but going to come back really useful when we start doing transformation of random variables. And I will see you for lecture 11. Thank you very much.